In our last class, we discussed about structural analysis, right? And we tried to understand what actually analysis is all about. And now, today we'll be solving few problems which deal with the actually free body, how to draw the free body diagram, and then how to use the equation of equilibrium, which we are quite familiar with because we have been doing problems on equation of equilibrium from last many classes. Now, with regard to this chapter, with structural analysis, it's quite large in its extent. So, firstly, before going towards solving the problem, I would like you to understand what actually support reaction supports are. What are the various types of supports that we will be dealing with? Right. Firstly, we have a fixed support. Now, with regard to any fixed support, for example, if this is the cantilever, it's usually fixed on only one side of it, it's free on the other side. So now we here need to understand what does this fixed and do, what are the reactions that is it is going to provide. It will simply, it will be having, as you already know, it will be having a vertical reaction, it will have a horizontal normal force, and it will be having a movement, right? All the three are resisted. They are resisted, they are resisted, they are resisted. It's your movement, M, your shear, V, and your normal force. There you have to calculate all three of them, right? Many a times we don't calculate normal forces because value is quite negligible. So we don't consider calculating this. The primary thing is that we need to calculate a shear force and moment. Now, why have I put the cross against it? This means that these forces have been resisted, right? Have been resisted. Resisted. What can you resist? Whenever we are somebody applies a force to to move us. For example, our body is a standstill. We are standing somewhere, and someone has started pushing us. Until and unless, for example, if we had to put a force of 10 kilonewton, I also need to give a reaction of 10 kilonewton so that I will not be able to move. Now, if the force from the external source is more than what I can resist, what will happen? I'll fall. Simple. Now, as per the equation of equilibrium, the amount of movement that is actually coming, let's say it has some load W. Now, because of this load W, there will be a movement. There will be a movement, right? There will be a movement at point A. Now, at point A, I need a movement resisting reaction, right? Now, this will be your resisting moment. This is your resisting moment, which we have to calculate, right? And similarly, if I have a reaction of, let's say, P at the point A, similarly, I should be having a resisting reaction at the same point so that the structure is in equilibrium. It should also be equal to P. So this is how we actually calculate. And normal force, again, if I am being provided with normal force N, I would be having a resisting N as a normal force. Now, this was with regard to the fixed support. Then we will be dealing with pinned supports or hinged supports. Now, what does this pin support or hinge support mean? Whenever you are providing support such that it's being, we show pin support like this. And now, how is it different from fixed support? What happens at the pin support? It will certainly have reaction, resisting reaction, fine, and it will also have horizontal normal force. But what will happen to the movement? Let's say this was the movement. It will release it. It will release this movement because being the hinge portion at its center, whatever movement comes on this side, that will be released on this. No resisting movement will be there. No resisting movement. Only you will be having two translations. One will be horizontal one, or you can call that as normal force, and it will be vertical one. You can call this horizontal normal force. Vertical one will be shear force. Therefore, you can simply say at any hinge, you will be having on two translations, two unknowns. Simple. You have to calculate the value of two unknowns. You have to calculate the value of V here, and you have to calculate the value of N here. Okay. Now, the third one is roller support. Now, what does the roller support mean? Third one is your roller support is usually shown like this. How is this different from the other two support conditions? Firstly, movement that is there, whatever movement is that, that's allowed because of this bend. Now you will be having a vertical reaction, it will be resisted. But again, here the translation, horizontal translation will be now raised, right? Because you have these roller support there, it will allow you to go to and fro. Therefore, while allowing it to go to and fro in the horizontal direction, we can simply say it will allow the horizontal translation. Therefore, what we have here is only shear force V, which is vertical translation. And there are vertical translation. Or we can call that as shear also. That is shear also. So this doing in our last class on the basis of that cantilever. We'll solve one problem. We have a cantilever and we have a number of loads on it, point loads. We have point load 1, we have point load 2, 3, 4. We have 5 point loads on it, right? And point load 1, point load 2, load 3, point load 4, point load 5. And all of them are at equidistance. They are at 1 meter apart. Say this is 1 meter, 1 meter, 1 meter, 1 meter, 1 meter, with the intensity of 5 kilonewton load. at every point. 5 kilonewton, 5 kilonewton, 5 again, 5 again. Okay. Now, if we have to find the uh, internal shear force and the moment at section, let's name that as, let's say this is your point A and this is your point B, and let's add one more movement at this point. We have another movement at the end of the cantilever, that is at point B, which is 20 kilonewton meter. Okay, these are the loadings on any cantilever. We have combination of point loads and we have a movement at its end. Now, let's say what I need here is uh, I want to know shear force at this point, right? And mention 2 points here. Let's say this is your point C and this is your point D. I want to know what actually happens at point C and what actually happens at point D. Okay, they are almost at the same point, but one is on the right side of this section which I have drawn. It is here, and another is on the left side of this section. Now, what I need to understand here is I want to know whether the shear force or the bending moment are same at these both points. At the both points. Now, this C point is actually this C point is actually on the load of P. It is almost on that point. It's on point where I have applied a 5 kilonewton load, and the another one is somewhere apart from point C. Okay. Now, what I need to understand here, I want to calculate its shear force and moment at point C and at point D. Now, here what I could say is both the points are almost on the same point, almost on the same point, but there can be some differences. Now, what are those differences? Let's say first of all, what we have to either check for only one side of the cantilever. We can do that by drawing the free body diagram of the segment to the right of the section. Let's say we are considering this portion that is to the right of the section. So here it will be your beam is like this, wherein for segment CB, for segment CB, your loads are 1, 2, and 3, and then a moment. This is for segment C and B. Okay. Now we already know that why have we chosen the right side? We can choose either. We can choose either left or we can choose right. Now, such that in order to choose the left one, I should be knowing all the reactions that are here at the fixed end. So, if I want to get into if I want to get into something wherein I want an easy solution, I will simply say I'll choose the one where I have to do lesser amount of calculations. Now here I have chosen the right side of that point C. So, and I have another segment which is now DC. This is CB, and I have another segment which is DC now, which is DC. If you can see clearly at point DC, there will be now one more load added at point D, which earlier was not there when we were talking about point CB. Here at point C, load is on the point C. Remember that. Load is on the point C. That means this load is on the point C. But while I'm calculating it, actually, I cannot consider that load which is at point C. Once I will move towards left, the moment I have moved towards left, leaving the point D, and at the point which is quite near to the point C, then I have to take into consideration this 5 kilonewton load which is there. Okay, 1 meter, 1 meter, 1
सर डी
meter.
और सी के बीच में कहाँ इतने लोड्स हैं?
Huh?
डी और सी के बीच में कहाँ इतने लोड हैं?
डी और सी में तो कुछ भी नहीं है.
सर आपने लिखा ना डी और सी के बीच में आपने 4 लोड्स रखे.
अच्छा, डी एंड सी. हाँ, in earlier case it was only three loads, that is load 1, 2 and 3. Fine. Now the moment I have moved towards D, that is from C to D, then the point that is very near to the point C, there is a load. This is the load here, this load that will get incorporated now. Do you understand now?
फिर यहाँ पर डी और
वहाँ पे जो सी पे है.
हाँ, फिजा फिजा ज़रूर बताइए.
सर ये डी और सी है यहाँ पर कि डी और बी जो आपने 4 लोड्स लिए, दूसरी सेगमेंट जो आपने ली है.
No, it's D and C. It's now D and C, this portion. Sorry, D and B, D and B. D and B, it's D and B. Now it's okay?
हाँ फिर ठीक है.
It's D and B. Only one load has been added. That is because I have moved from point C to point D, which are very close to each other. But the moment I have left the point C, then the consideration of the one more point load, 5 kilonewton, will get added up now. Is it clear now?
Yes, sir.
Okay, now we have two segments here. I would like to check what happens actually at point C and at point D, which they are almost at the same point. You can say it, they are almost at the same point. But in case 1 and in case 2, the difference is only that in case 1, point C is that point where there is a point load 5 kilonewton, and the point D is that point when I have left the point C to and I have moved towards D. The first point that is there, that point is D, and in that case one more load will get incorporated. Okay, now we have to consider both the equations and try to solve them and check what is the shear and the movement at both of the segments. Let's say, for example, firstly I am taking the segment C and B, and I'll see what actually is there, keeping this in consideration that let's say our normal forces are almost negligible. We won't consider normal forces. Okay, so here what we can do at point C. Now, what are the values that are there at point C? We will be having a shear V, right? We will be having a normal force, which we are actually not considering here. Okay, and we will be having a moment. Let's say this is the direction of movement. We don't know yet what will be the direction of movement, which we have drawn to be a clockwise movement. This is an assumption. I assumed that, let's say, it has a clockwise movement. Now I need to check what? I need to check two things, that is V at C and movement at C. Two things. Now in order to calculate V at C, we will say summation of forces in Y direction. Let's say positive upwards is positive. We assume that we make a convention that upwards vertical force is positive and downwards will be negative. Therefore we can simply say here your VC minus 5 minus 5. Just give me a moment. हाँ जी. मैं क्लास दे रहा हूँ.
So you're not audible. You're talking to us. So you're not audible.
Is it clear now, sir?
No, sir, you're not audible.
What is the issue? Now what? Okay.
Yes, sir, better.
Okay, so now firstly what we have to calculate, we have to calculate VC, and we can simply say VC is in positive direction upwards. That means VC minus 5 comes at 1. We have three loads, that is 5, 5 and 5. That will be your VC is how much? 15 kilonewton upwards, right? Your VC is 15 kilonewton upwards. And then we can calculate movement at C. Let's say positive is anti-clockwise here. Give an assumption. This isn't just a sign convention which you can yourself draw. Let's say at point C. Now movement at C, it will be certainly, now I have drawn it to be a anti-clockwise direction. Sorry, clockwise direction. Therefore, clockwise will be now negative. It will be negative. Minus MC, and then what movements will be due to here. That means
You're not audible, sir. So we don't hear a thing.
uh, minus Sahil, has it improved somewhat?
Better now.
Is it better now? Sahil, shall we start again?
Better now. Yes, sir.
Okay. So now we were talking about the movement at point C. Now, as you can see, we have a notation of anti-clockwise as negative. So if you will see your movement at point C, that is in clockwise direction. This is in clockwise direction. Again, the movement at point 1, this is again clockwise, clockwise. clockwise, and you can say all of them will be having a sign of negative, right? That will do. Your movement at C is actually how much? 5, it's 20, 30. Okay, it's 50 kilonewton meter. Direction is minus. This assumption, getting the value of minus, this means that the assumption which was actually what you have assumed that it is a clockwise movement, but it came out to be negative. Therefore, you can say actually it is anti-clockwise. The movement at point C is anti-clockwise of magnitude 50 kilonewton meter. Simple. Then we have for segment DB, you can again calculate the summation of forces in y direction. Again, notation is positive upwards. Therefore, you can now calculate your, again, you will be having vertical, you will be having horizontal force, and you will be having again a movement at C. Movement at D. No, sorry, now it's D. We are talking about D. Movement at V. Shear force at D. Now summation of forces in y direction is equal to, as actually 0, which is equal to, now it will be VD minus 5 minus 5 minus 5 for 5 magnitude point loads, that will be equal to 0. Therefore, your VD will be equal to how much? 5, 10, 20. 20 kilonewton. So see the difference. See the difference here. Now, when you have to calculate summation of forces, sorry, movement now at D, that will be again equal to 0. Now, notation is anti-clockwise positive. Therefore, you can say, now in order to calculate the movement at D, it will be again minus times MD, because minus, why is it minus? Because we have assumed it to be a clockwise, but notation is anti-clockwise positive. Therefore, minus MD minus 5 into 1 minus 5 into 2 minus 5 into 3, right, minus 20. That will be equal to 0. Therefore, you can say here your MD comes out to be again same, minus 50 kilonewton. Now try to compare the both movement and your shear. You have same movement on either side of the line. Let's say this is your line A dash. You have same movement on the either side of the line AA, but you have different shear force.
सर एक्सक्यूज मी सर
Yes,
सर यहाँ
yes,
पे
Sahil, tell me.
सर यहाँ पे 4 मूवमेंट्स आनी चाहिए थी ना, क्योंकि 4 फोर्सेस थे ना डीबी में.
Okay,
एमडी
fine.
माइनस
यहाँ
5
पे
मल्टीप्लाई
4 movements. Okay, listen, Sahil. यहाँ पे 4 movements क्यों नहीं आई? Why didn't we consider this? Because movement जब भी हम लेते हैं, we take the value of the force multiplied by the lever arm, multiplied by the distance.
डिस्टेंस 0 देयर.
But here distance is 0. Yes,
ओके
that
सर.
is why this movement due to this load is not actually incorporated here. That is
Okay,
why
sir.
the movement has remained same, right? But On the contrary, only shear force are different on either side of the frame. I hope it's clear
Yes,
now.
sir.
Okay. Now let's say we have one more problem, which is a simply supported beam with the same intention to make you understand more. Let's say now we have again a simply supported beam. It's having a roller support on one end, and it has a pin support on the another end. Okay, and then it has a load of 6 kilonewton at point 3 meter from, let's say this is point A, it is 3 meter, and then the rest of the distance is 6 meter. Okay, now at the same point here where we are talking about this point where we have load, we will again see, let's say we have 2 points. We have one on this side and another on this side. Okay, we have 2 points here again. That is, let's say this is A, this is your B, C, and D. Now again, you will have to choose one side of it. You need not to choose two sides. And one more, there is a movement here, 9 kilonewton meter at point D. At point D. Now here you can simply say, now drawing its free body diagram, you will be able to draw its free body diagram by what is the reaction at roller support? Can anybody tell me? It has only vertical translation, that is A Y, and at end B it will be having D Y, right, and it will also have dx. At pin support we have two translations, horizontal and vertical, right, and then we also have a movement of 9 kilonewton at this point, and we have a load which is 6 kilonewton at a distance of 3, and this is 6. Okay, now this is with regard to the external loadings on this simply supported beam. This is a simply supported beam. This is, we have not incorporated any fixed beam here, so that is why this is called as a simply supported beam. Now, in order to first calculate what will be the reactions at two different points, what are the reactions? That is AY and DY. Before we can solve the either side of the problem, that is either this side, either right side, right half, we will solve it taking into consideration either a right hand side of the point from where we are calculating, or we can take the left hand side. We can take only one and solve it. Before that, we should be knowing the reactions. In order to calculate the reactions of this free body diagram now, I'll take summation of moment at let's say D is equal to 0, and taking again anti-clockwise positive. The sign notation is anti-clockwise positive. Now when I have to calculate it from D, that means it is the point here at point D. I can simply say that what are the loads that I have? I have firstly 9, which is again, what is it? It is a anti-clockwise. Okay, it is anti-clockwise. That means it will be positive, simple. And then I have this load, which is 6 kilonewton. 6 multiplied by 6. It is again which direction? Anti-clockwise, positive. Okay, and then I have this ay multiplied by 9. What is the direction? Clockwise, that means negative. That will be equal to 0. And your ay will be, calculate the value of ay quickly. Tell me the value of ay.
The 5.
Okay, ay is your 5 kilonewton. Ay is your 5 kilonewton. And how much will be dy?
1.
Absolutely 1. Total of 6 as point load. If ay is taking 5, similarly, your dy will be taking as 6 minus 5, 1. Okay, here now we will consider the left part of the simply supported beam, which is A to B in first case, and then in second case, I'll consider A to C. I have to see what actually happens at point B and at point C again. It is a similar situation which we already had. Then in that case, firstly, checking the on the basis of equation of equilibrium, for segment AB, summation of forces into X is 0. Okay, summation of forces into X is 0 because here, what are the reactions that we have? We have vertical reaction here, which is how much? It is AY is 5 kilonewton. And then you can say we have a vertical shear force at end B, which is VB, and we have a normal force, which is NB, and we will be having a moment also. We will have a moment for which I have given a direction of anti-clockwise, that is MB. Okay, and again similarly at point A and C, I'll be having vertical reaction of 5 kilonewton here, and then it has a distance of 3 meter, both has a distance of 3 meter, they both are 3 meter. And then at point C, now the load has been incorporated again, which is how much? 6 kilonewton. Okay, and it will be having, at this point it will have VC, it will have NC, and it will have a moment MC, moment at C. Now I have to calculate what will be its VB. In both the cases, I have to calculate all the values. I have to calculate VB in first case, I have to calculate movement, and similarly, I have to calculate movement at C, and I have to calculate VC. And here, firstly, our Fx is 0, no horizontal force is there. So now that if the load 6 kilonewton would have been inclined to some direction, let's say it would have been inclined at a degree of 45, 6 kilometer, then in that case we would be having in x direction because there would have been one component in the horizontal direction also. Now that we have simple perpendicular load, therefore we can simply say that there are no horizontal forces on this beam. So forces in x is 0, and then summation of force in y is again 0. Therefore, for calculating that, it will be simply 5 kilonewton, that is VB minus VB. Your that is equal to as 0, and you can say VB is again equal to 5 kilonewton. It's simple. simple. अगर यहाँ पे 5 kilonewton at point A है, it will be VB will be also 5 kilonewton on the other end. Then we have to calculate movement at B is equal to 0. Right, movement at B is equal to 0. So calculating the movement at A, therefore we have one is 5 kilonewton multiplied by 3, and then that will be in which direction? It will be clockwise direction. We have anti-clockwise positive notation. This will be minus, and then we have this MB, that is 0. Therefore you can say your movement at B is equal to 15. Your movement at B is equal to 15 kilonewton meter. But it's positive now here. Keep this thing also in mind. It's positive. Therefore, you can say the assumption that we had made at point B, that the movement is in anti-clockwise direction, is true, is correct. Okay. Okay, now we will be dealing with which segment? One more segment, which is AC. Segment AC. What are the unknowns? Firstly, summation of forces into x0, summation of forces y0. For that, y summation of forces, which is we have 5 kilonewton forces, and then we have 6 kilonewton, which is from the top. Then we have VC, that is equal to as 0. Therefore, you can say VC is equal to as -1 kilonewton. And we have summation of forces again, summation of movement in at C. Summation of movement at C is equal to as 0. Again, notation anti-clockwise positive. Therefore, in order to calculate the movement at C, we will be having what? Firstly, we will be having MC minus 5 cross 3 is equal to 0. So here you can write movement at C is again 15 kilonewton meter. Okay. So you can see here in both.
So,
Shall we?
yes, sir.
So in our previous case also, we saw that movement was same on either side of the beam, but on one side of the beam, we had a shear force of 5 kilonewton, right? For segment AB, we had a shear force of 5 kilonewton, and immediately towards the point C, we have a shear force of -1, right? That actually, if I had a shear force of 5 at point B, now a downward force of 6 kilonewton has reduced the shear force from 5 to -1. That is 5 minus 6 is -1. It goes down, it goes in the negative direction. And let's do one more problem. Now, let's say we have a cantilever again, and it has a uniformly varying load. Now, it has a uniformly varying load of uh, here it is 1200 Newton per meter, and this is your point A and B. And what we need to know, we need to see the shear force and bending moment at point, let's say C, any point C. It's C, and it's at a distance of 1.5 meter. Here again it is 1.5 meter. I hope you will be able to do this yourself. Will you be able to do it? Will you be able to tell me what is the shear force at point C? It's a simple one. Yes, Fiza, Zuhur, will you be able to do it? Calculate shear force and bending moment at point C.
कॉपी नहीं कर रहा है.
Yes, sir, I'll try it.
So where is this force acting of 12,000?
It is at this point, at the top point, 12,000 Newton per meter. Or you can say it is intensity at this point. You can calculate the intensities at different point now. Will you be able to calculate intensities at different points also, like we have here C at point C? Okay, fine. Let's do it together. Firstly, what we need to know here is I need a moment and shear force at point C, which is here. Now for that, I need to know what will be the intensity of load at this point. I need to know intensity of load at this point. Actually, I have got intensity of load on this end, on the top end of this triangular uniformly varying load. In order to calculate the moment at which point, at point C, I need to know the intensity of loading at point C. I'll do that by simply using similar triangles. I have two triangles now. One is, let's say this is ABC, this is your D and E. We have two triangles in order to calculate the intensity of load. So I'll do it this way by similar triangles. It will be 1200 divided by, let's give it a name WC. WC is equal to is equal to 3 per half and half, that is 3 1.5. So your WC will be equal to 1200 multiplied 0.5 by 3. Calculating it, it will be 5, 5, it will be 600 Newton per meter. Sahil, is it clear how it came out to be 600 kilonewton at point C?
So
Sahil,
WC
is
क्या
this
है?
clear?
DC.
WC is intensity of load at point C. Load intensity
हाँ ठीक है सर. हाँ हाँ क्या समझ.
at point C, जहां पे आपको निकालना है. By similar triangles आपने निकाला. There you have seen the intensity of load is 600 Newton per meter. Okay. Now you can simply calculate what? You can simply calculate your shear force and bending moment diagram. Okay, fine. Now again, here you have to check movement at point C. You will choose either of the side. You will choose either left side or you will choose right side. For us, convenient would be to use the triangular portion, which is this one, and it has a load this way. Fine. It does not have any reaction at point B because it is a free end at that point. If we would consider the left hand side, we have to see the complexity in choosing left hand side. Firstly, we should be knowing all the reactions. All firstly, we have to calculate vertical, we have to calculate normal, we have to calculate what? We have to calculate movement also. Then again, we need to calculate the area of the loading in this pattern. It is again complex, right? So simpler one is to choose the right hand side. So here again, as per the equation of equilibrium, summation for this very point, we will be having vertical, we will be having a normal and a horizontal. and we will be having a reaction, sorry, movement. Okay, and we already know that at point this we have a intensity of load 600 newton per meter. Okay, we will be having a load of 600 newton per meter. And then you also need to know, if you want to calculate, chalo, we will do that later. Summation of forces into x, no force is in x, that means it's 0. Force is 0. Summation of force into y, that will be what? At point C, you will be having VC, you will be having MC. VC minus load pattern, area of the diagram, load. Load is half of base. How much is base? It is 1.5, and altitude is how much? 600. That VC out to be 1 300. That means it is 450. 450 shear force C. So summation of movement at point C is again 0. So giving the equation, when we have movement at C, we will be having movement here. We have assumed to be clockwise. That means here again is anti-clockwise positive. Is minus times movement at C. Okay, minus the load. How much is the load? Again, half of base into altitude 6 into centroidal distance. How much will be the centroidal distance from C? It will be, as you already know, how much is the centroidal distance from C? Can anybody tell me? Can anybody tell me that? We usually take this as 2 by 3 or 1 by 3.
1.5. 2 by 3, 1.5.
2 by 3
मतलब
of
prop
x, and this portion is 1 by 3 of x, or L. And 2 by 3 is 2 divided by 3 multiplied by, how much is it? 1.5, or it's 1 by 3. This is vice versa.
by 3 लेने हैं हमें 1 by 3 or 1.5.
It is 1 by 3 from C, and 2 by 3 is the rest portion. Is this correct now?
Yes,
Is this
it
correct?
is 1.5.
Yes, 1 by 3, 1 by 3 multiplied by 1.5. Okay, therefore we can see our MC is equal to, and what else is there? Is there anything else? No, there is nothing that is equal to as 0. 1 by 3 is actually of 3, that is 0.5. 1 by 2 multiplied by 1.5 multiplied by 600 multiplied by 0.5. So your MC comes out to be, is equal to minus 225 minus, why is it minus? In the other direction. That means it is actually in
तो ये क्यों आएगा माइनस माइनस माइनस
this direction.
कट हो जाएगा
Minus नहीं है.
नहीं सर दोनों नेगेटिव है
No,
ना
this is in positive direction. They are both negative. This is positive. Sorry. Is it correct? 225. Have you calculated it?
नो सर नॉट येट
Yes, it will be 450 into 0.5 225. Okay. हाँ.
सर ये माइनस ही होगा ना
कैसे होगा माइन?
Of course, it will be minus.
माइनस होगा।
Sahil, it will be minus.
तो दोनों नेगेटिव है ना?
हाँ, तो एक
माइनस एमसी
एक को लिया ना दूसरे साइड से, एक
ओके हाँ
एक
हाँ
को अगर आपने दूसरे साइड से लिया, एमसी हो गया पॉजिटिव, बाकी वो वाला तो नेगेटिव रह गया ना उधर ही।
हाँ जी।
ठीक है, इट विल बी माइनस। Okay, this is your movement at point. This minus means the direction you have chosen, which was earlier to be clockwise, is now anti-clockwise. Now we will be doing we will be trying to see what actually happens when we have to calculate the shear force and bending moment diagram, taking the function of x, when we take it as a function of x, because here for example in our previous all three of the problems, we were told to see that what is shear force or bending moment at a particular point. Let's say here we talked about point C. In previous cases we talked about a particular point. Now that if we have a such that we have to draw the shear force or the bending moment diagram of the complete beam, that be a fixed, that be a simply supported, that be a frame, whatever it is. In that cases, what we have to do, we will have to draw the shear force diagrams in any of the beams, whether that be a simply supported, a cantilever, and we see that the shear force and the bending moment varies along the length of the or along the span of the beam. And we need to check what actually how the diagram shear force or the bending moment diagram is throughout the section of the beam. And these variations, which is for bending moment and shear force along the beam axis, is basically done by the method of sectioning, as we have already discussed that method of sectioning. We do that by method of sectioning. Okay, and in such cases, how we do it actually, we make a arbitrary distance, let's say at point any x, from one end of the beam, and then we apply a simple equation of equilibrium to the segment, and then solve it for x. X is the complete span of the beam. Okay, and making the v and m as function of making shear force and movement as function of x, as function of x. Here the internal shear and the bending moment function will actually be discontinuous. It won't be continuous because shear force will vary along the length and the movement will also vary along the length, and their slopes will also be discontinuous here. It won't be a continuous one at any point, whether that be a distributed load or a concentrated load or even a couple. Because of all these loads, there will be a discontinuous shear force diagram and bending moment diagram. And because of these functions, it must be determined for each segment of the beam, which are actually located between any 2 points. Let's say, for example, I'll show you with the help of an example. We have this beam, simply supported beam. It has pinned support on one end, and it has a roller support on another end. And it has, let's say, a point load. It has a uniformly distributed load of intensity, let's say W per unit run, which is for a distance of, let's say, A. Now, I want to know how the pattern of the shear force and the bending moment varies. Now, for that, I have to make the equation of shear force and equation of bending moment function of x. Let's say in that case, what I do for when I have to calculate it, let's say this is your point A, this is point B, this is C and D, and so on and so forth. The total span is your L. A is the span of uniformly distributed load, and then B is actually the distance from the point A and the point C where we have uniformly distributed load. So how we will make it as a function of X now? What we will do here is, uh, because being the discontinuous throughout the beam, we will be having different shear force and bending moment diagram. What we will do now, I will be having a different shear force for this element. I will be having different shear force for this element, and I will be having different shear force and bending moment for this element. Right? I am actually having three segments of this beam where there will be a discontinuous shear force and bending moment diagram. Now, how will I deal it with? I'll have to do firstly for your span AB, I'll make a distance of x1. This is the distance of x1. It is somewhere in between A and B. It is not up till the end of the A. What I say, let's say we consider a section X between A and B. Let's say that is somewhere here, and integrate it then between the limits, that is 0 to A or A by 2, wherever I want to find out the shear force or the bending moment diagram. I consider it, I say that at any section A, x1, which is at a distance of x1 from A, and that will be my equation for x, and draw its shear force and bending moment equation. And then for point B and C, I'll say, let's say I consider a segment X, I consider a segment X at a distance of x2 and draw its equations, that is shear force and bending moment diagram. And for third portion, that is this one, it will be x3. I will be having different shear force and bending moment equations, and then integrating it within the limits will give me the shear force and bending moment diagram. And then I can simply plot the shear force and bending moment diagram. For example, here if I have to draw the shear force and bending moment diagram, it will simply be somewhat like this. At point A, it will be positive. If you remember, I had said when shear force is positive, when it moves in which direction? Clockwise direction. That means it is going clockwise, it is positive. It is positive. This portion will be positive 1 and this portion will be negative 1. This is a positive shear force. This is positive shear force. Therefore, at point A, I will be having some value of shear force, and at point B, let's say this is point B. Now, if this is uniformly distributed load, therefore it will vary somewhat like this. And then we will be having a constant shear force up till C. That point will be C. And then towards the D, it will be negative. It will be the negative values. Now we will be drawing many other shear force bending moment diagram by which you will get a clear picture how we actually draw the shear force and bending moment diagram. Whenever I have to draw the bending moment diagram, at point A I will be having zero moment, at point D I will be having zero bending moment diagram, and then have bending moment diagram up till let's say this is your point B and this is your point C. Up till point C, I will be having point B, you will have a parabolic variation of shear force because uniformly distributed load, and then you will have a linearly varied bending moment up till this point, and then it will go down to point B. This will be your bending moment diagram. This will be your shear force diagram. This is again now that you had made this as positive. Why? Because this is a sagging bending moment diagram. No hogging is there. Sagging bending moment diagram. We don't have any hogging bending moment diagram. As I have already said you, when movements are such that it will tend to bend it in such a way you have convex upwards. This is your positive movement, and then you can have movement such that it makes it hogging. That means in that case it is negative. We'll solve a simple quick problem where we can deal with the beams by just making the equations and then drawing it shear force and bending moment diagram. Let's say I have a simple simply supported beam, again roller, pinned and roller, and then I have this point load at 5 kilonewton meter, and it has a distance of again same 2 meter and 2 meter. And if I have to draw its shear force and bending moment diagram, what will I do? As per dealing the beams as a function of x, as a function of, I'm drawing it as a function of x. Simply, I will be having this reaction. Firstly, I'll name it A, B, and C. Firstly, I'll choose between A and B. Firstly, I'll choose segment which one? A and B. I'll choose segment A, AB. And I'll say, let's consider a section X at a XX dash at a distance of X from point A. And then I'll say, my reaction will be V will be simply, this is my V at this point, it will be, if 5 is the load, how much will be the reaction carrying by each of the support? It will be 2.5 will be here, and this will be 2.5. My V will be simple 2.5. And how much will be the movement? It will be 2.5 times X. Simple, 2.5 times X for segment AB. Now, when I consider this whole segment and I say, now consider a section A dash at a distance of X from point A. Then in that case, my movement will be, sorry, shear force will be firstly summation of forces y is equal to 0. My shear force will be 2.5 minus 5, this load, right, minus V, therefore is equal to 0. This will be, now you have load this, you will be having a shear force, you will be having a moment. Here again you had a moment also M. You calculated V, you calculated M. Here again you have V, you have M. Now for this segment, which is somewhere in between B and C, that shear force V will be equal to minus 2.5 kilonewton, and our movement will be summation of movement will be equal to 0, anti-clockwise positive. Therefore, you can draw the shear force bending moment diagram. That will be M, is your anti-clockwise. That means it will be positive. Plus 5. 5 means 5 into distance. Now distance is how much? X minus 2. This we have to deduct this portion. That means x minus 2 minus again which one?
ये दोनों
uh,
कहाँ x हो सकते हैं? इससे पहले भी हमने x लिया था
sorry,
ना?
a bit louder.
तो ये दोनों x कहाँ हो सकते हैं? इससे पहले भी हमने x ली थी ना डिस्टेंस?
हाँ, तो मैंने x माइनस 2 लिया है ना, ये वाली डिस्टेंस डिडक्ट की है ना, इतनी 2 जो 2 थी।
तो पहले हमने ली ना x डिस्टेंस फ्रॉम a टू, जो आपने वो लाइन की ड्रॉ अल्फा अल्फा डैश।
बिल्कुल, मैंने दैट इज कंसिडरेशन, आई हैव कंसिडर्ड डिस्टेंस सेक्शन xx एट द डिस्टेंस ऑफ x, मगर एक्चुअली मुझे किसका देखना है? b और c के दरमियान का, नॉट a और c से। ये मूवमेंट मैंने किसका निकाला? सेगमेंट, जब ये ए बी था। अब मुझे किस सेगमेंट का निकालना है? अब मुझे किस सेगमेंट का निकालना है जो कि बिटवीन बी और सी है? ओके, बी और सी के लिए मैंने कंसिडरेशन क्या किया? मैंने सिमिलर कंसिडरेशन किया, एक्स फ्रॉम पॉइंट ए टू द सेक्शन ए, मगर एक्चुअली वो कितना है? एक्चुअली वो इतना ही है, विच इज एक्स माइनस 2, जो बाकी का रह गया। समझ गए? minus 2.5 is the reaction at this point into x is equal to 0. Is it clear? The movement equation? So calculating it, this will be your equation for movement, will be m will be here, will be 10 minus 2.5 x. This will be your equation for movement to be calculated depending upon your values. Now give you the values when x is equal to as 0, when x is equal to as 2, and when x is equal to giving the values when it is 4, and it will give you the actual values. Now drawing, you can simply draw it shear force diagram by, we have a vertical force of 2.5 at point this, and up till point B it will be same, and at point B you have a 5 kilonewton. That means it will go down to minus 2.5, minus this is 2.5 here, and at this point again it will be 2.5. Shear force diagram. Okay, and similarly you can draw its bending moment diagram also, and you already know for this point value your bending moment diagram will be, it's a sagging moment, be a straight line, it will be a linear, it will be linear, but your movement will vary for this very portion as m is equal to as 2.5x, 2.5x, and here your movement equation will be m is equal to as 10 minus 2.5x for this very portion. This is for this portion. And your maximum movement will be at which point? At this point. You will be having m max. You can easily calculate that m max. That will be, m max will be how much? It will be simply 2.5 multiplied by 2. 2 is the distance, that is 5. This is equal to as 5 kilonewton meter. 5 Newton meter. No, it's kilonewton. Kilonewton. Now, if you have a maximum movement of, here you can see you have a maximum movement of 5 kilonewton. Why is it so? Because there is a reaction of 2.5 that multiplied by the distance 2, it gives you 5. Now, this variation, this linear variation will give you different values at different points, like this point. Firstly, you can give the value of movement as this movement in the left portion when x is 0. When x is 0, movement is 0. Simple. Right? When x is 0, movement is 0. And when x is 1, movement will be 2.5. That means here 2.5. And it will vary accordingly, linearly, giving the values of x. Here again, in the right hand side also, you can give the values of x, you can give the values of x, and you can simply calculate the movement.